Welcome back, guys. Well, it has been a while since we haven't done the lecture here. Okay, so last time when we were having this lecture, we learned about driven oscillations and resonance frequency. That was for chapter 14. So for we are going to start chapter 15 today. So the chapter 15 is about traveling waves in sound. So the purpose of this chapter is to develop a general description of a wave that could be applicable for a variety of situations. What are the varieties of situation? Like, meaning, in what cases can we apply the description of the wave? We could apply it to, mechanical waves, water waves, electromagnetic waves, matter waves, etc. So before I start talking about all of these things, let's look at the word here, keyword. Wave. What this word wave means to you? Think about what, in terms of your experience in day-to-day life. What does, when somebody say wave, what does it remind to you of? Or when was the last time you have heard this word wave in your, day-to-day life or in general? So right now I'm talking, guys. That's also type of a wave. See? Hey, see? I'm talking, I'm doing something, some phenomena associated with this is described as a wave, okay? I'm talking, I'm producing sound, right? So what wave is, really? We don't really know what wave is, but we describe a disturbance in the medium as a wave, okay? So disturbance in the medium. So now it will be easy, right? So if we call this phenomena where there is a disturbance in the medium, we call that wave. Then we can now look at a different situation where we can see the disturbance in the medium. One of the example I already told you is, right now I'm talking here, this is a sound wave. You can also scream across your room right now and then produce a sound, okay? That's a sound wave. Sound wave is also disturbance in the medium. Medium for the sound wave is air, okay? Now water, right? You guys are familiar with water. If you go in the river or in the ocean, and if you put like a stone, what happens? You will see ripples, right? So that's also a type of the wave there. In that case, the medium would be water, for a water ripple. Mechanical waves. So mechanical wave, how do I say what mechanical wave is? Mechanical wave. So some type of wave needs a medium to travel, okay? some other wave doesn't need a medium. So whenever we need this medium, we call that as a mechanical wave. Okay. So as I said, sound is type of mechanical wave because we need air is a medium for sound wave to travel. If you go in vacuum and you can scream like hey, and then it becomes just like that, no sound will produce. Okay, basically. So that's a mechanical wave. There are also other wave like electromagnetic wave. Electromagnetic wave example is light. Light is also electromagnetic wave, and then there are other type of wave like matter waves, etc. So these are the few types of wave. You can also produce a wave during, like you could also see the wave during earthquake. Okay. What else shall we talk here? Okay, so traveling wave. So we know now wave. What is now traveling wave? So the word traveling wave see, I'm used to writing double L here, so I'll just leave that way. This is how I learned in British English. I think in American English there is only one L here. So traveling wave. Again, as we said, wave is a form of a disturbance, in a medium. So traveling wave is a form of the disturbance in the medium with well-defined speed. Okay, so there is a well-defined speed of this disturbance in the medium that we call traveling wave. And then sound, we'll talk about sound in the next lecture, not today. So that's for another lecture session. Alright guys, so that's the beginning of the wave, traveling wave. So okay, so before I start deriving equation here, I wanna say a few things about some of the concept we need to describe the wave. So let's say we have a wave. Let's say this is the distance x. It's traveling x meter. Let's call this, we have y meter. That's the, and then we've got something like this. So this for the wave, that's that is exhibiting simple harmonic motion, meaning it's really repetitive over time, right? Repetitive over a period of time. We can specify a few things. So amplitude is the maximum displacement here from this position here. So this is the A, amplitude. Amplitude. Okay. So this is the maximum, this part here. Okay. Amplitude, you guys learn about the period in the simple harmonic motion chapter. Here you learn something called wavelength. Okay, so this distance here from really, let me draw it in the color, from here all the way to here, this whole distance that the wave travels in one period is called wavelength. Okay, so this distance here we can give it as name lambda. since this is a distance lambda, lambda is now wavelength. Wavelength represented by lambda, Greek letter lambda, okay? Maybe I should write here Greek. Okay, so this guy here is lambda. Wavelength lambda, this is the distance, so the unit of lambda is meter. Okay, SI unit is meter. Alright, amplitude, you know, it's the maximum distance, right, from this equilibrium position here. So that is just what you learn in simple harmonic motion, you can just really apply here also. Amplitude, period, you guys know period is, you know, the time required to repeat that motion, right? So basically this is the distance we have here for one period. So the period is really the time at which the motion starts to repeat again, right? So that's the period, you guys already know. Whatever you learn about that period and a frequency, you should be able to use it in this chapter as well, okay, from simple harmonic motion chapter. Alright guys, so those are the important things. That's really the new is lambda here, wavelength. That's a new concept for you guys. Okay, so there is something called transverse wave and longitudinal wave. So if we have a wave traveling in this direction, if this is the direction of propagation of wave, propagation, I mean it's moving, okay, forward, it's proceeding. Let's say this is the direction of propagation wave, and if the particle oscillates perpendicular to the direction of propagation of wave, then it will be something like this, okay? Then this type of wave is called, so we have a particle here, this particle kind of just oscillates, so this type of wave is called transverse wave. Transverse wave. You may be wondering what is it talking about. I cannot visualize what this is. Let me show you guys. Okay guys, alright, I got this string here. Can everybody see this string? Okay, so I'm going to apply some tension, okay? See? You guys see, right? This is string. This string is oscillating, right? It has some, so it goes through disturbance, right? So disturbance here. So the particle along this string here, here, whenever these are kind of, or maybe we could also do is like kind of pluck and leave it. I mean, it's hard to do for me when I'm by myself. If I had it attached at the end here, and then if I were to kind of, pull, just pluck in the middle, then I would see something like this, okay? So this is like a particle there, okay? That dot here is like a particle in this string, okay? So this particle would move, it will oscillate perpendicular, right? So this is perpendicular to the direction of propagation of wave. Wave is actually, if we are to just fix one end and then just apply, some tension from the other end, we know the wave would travel that way, right? So the propagation of wave is this direction, but then the particle oscillates perpendicular to the direction of propagation of the wave, then that type of wave is called transverse wave, okay? Now, I'm going to erase this part here. There is also something called longitudinal wave. Example you learned about this, actual light wave is a type of a transverse wave. You'll see this as you advance in the semester. So longitudinal wave, so in the case of longitudinal wave, what happens is this. Right now I'm speaking, so example is a sound wave is a type of a longitudinal wave, okay? So what happens when I'm speaking like, see, hey, I'm talking here. What I'm doing is I'm making a disturbance, right? I'm bringing a disturbance in the medium. So because of that disturbance, you can hear the sound, right? So what happens when I speak is like this. There are air molecules in front of my mouth right here, right now. When I speak, some of the molecules are going to, they are just going to get really compressed, okay? Some of them are going to get really compressed, other are going to probably, go further away, like this, okay? Further away, right? You see the distance between the molecules far, these are closer, okay? So compress, this area is, let's say, compression, and this part here is rarefaction. R-A-R-E-F-R-A-C-T-I, and rarefaction, okay? So compression, where there is a higher pressure region, rarefaction is where there is a less pressure region, okay? So what happens here is, so whenever there is a disturbance, these molecules here, they oscillate in the direction of propagation of the wave here, okay? So here these molecules won't oscillate up and down. The direction of propagation is this way, direction of wave propagation. So here these molecules are actually also moving the same direction as in the, they are oscillating in the same direction as in the direction of wave propagation, okay? So they do like this rather than up and down here, okay? So this kind of wave is called longitudinal wave. Alright, so that is the important differences between transverse wave and longitudinal wave. Okay, so what shall I do next? Okay, so guys, I'm gonna do the derivation here. Let us see. Let me check this video. Alright, I'm gonna start the derivation in the next video, okay? So that way we don't have to switch. We don't have to we don't have to do the derivation in two different videos.